In this video, we're going to look at improper integrals, but we're going to look at families of functions and see if there's any common patterns we can derive from that. We're going to start with the integrals of exponential functions, and what we're going to do to make it a family of functions is not specify the coefficient up here in the exponential. And we know it's an improper integral because of the infinity sign here. That indicates that we're talking about the area as we head out towards infinity. In this case here, we're using t as our variable and e to the kt. Now notice we're going to assume that k is less than 0 for this. And the reason for that is only if k is less than 0 do we get an exponential decay curve. And in this case here, we're going from 1 in t all the way out towards infinity. And so we're talking about is the region underneath the exponential curve from here to here if it's an exponential decay. Fortunately, this is straightforward to compute, even with that k in there. We start off, as always, by applying the definition to handle that improper integral part. So we're going to integrate from 1 not to infinity, but to some upper level b. And when we're done, we're going to evaluate the limit as b approaches infinity. Otherwise, everything else stays the same. Again, all that's doing is setting up a temporary interval from 1 to b, and then once we've computed that, we push b out further and further and further. All right, then we restate the limit. This will be the last thing we evaluate. For now, we focus on the integral itself, and we know the integral of e to the kt is e to the kt again over k. If we differentiate that, we would get back to the starting exponential. And we're going to evaluate that between b and 1. So we keep going here, copying the limit down, and we're going to sub in the b and the 1 now. Keep the 1 over k out front. We'll have e to the k, and remember these are t values. So we're replacing the t inside the exponent there, minus e to the k times 1. And that now is pretty much done. There's not a lot of simplification we can do. So what we can evaluate now is what happens as b goes to infinity. As b goes to infinity, the only b is in this exponent here. In there we have kb, but remember that k is negative. That was one of the starting points to make the curve and the area underneath it make some kind of sense. So k times b is going to approach negative infinity, and then this entire expression, e to the kb, is going to be a negative exponential decay. As we push further and further out, that's going to approach 0. And so we've evaluated the limit. We have 1 over k, and we have our negative e to the k times 1, or e to the negative k. And if we wanted to, we could rewrite that as negative e to the k over k. Now at first glance, this might be a bit weird if you're thinking about signs. This looks like it's negative, but the area underneath this curve is positive. But just remember that k here is also negative, so this whole expression overall is a positive quantity. And notice it's also finite. So what we were asked to do was show that all the integrals of this type converge so long as we have that k less than 0. We use that as part of our limit calculations. The fact that it's finite leads us to the conclusion that the integral itself that we started with is convergent. E to the kt dt converges. With a little addendum, if k is less than 0. As long as we have e to the minus 2t, e to the minus 5t, e to the negative 0.1t, those will all have areas underneath them that are finite. Let's go through a similar argument with powers of t in the denominator. And again, all of these have the same kind of shape. They would have an asymptote at t equals 0, that wouldn't be defined, and then an asymptote horizontally as t gets larger and larger and larger. First step, we have an improper integral, we apply the definition. Integral from 1 up to b, and we'll put the limit as b approaches infinity with that. To make this a little easier to integrate, we're going to express this as a power. It's in the denominator, or t to the negative k, and so that's what we're trying to calculate. This we can integrate right away. We simply add 1 to the power and divide by the new power. We keep this limit out front, and we evaluate this at t equals b and t equals 1. Subbing in the values, keep this limit out front. We'll do it in a moment, evaluate it in a moment. Minus k plus 1, and then we have b to the minus k plus 1 minus 1 to the minus k plus 1. And we're pretty much ready to go. This thing is just equal to 1. The ingredient we have to evaluate or work with now is what happens to this expression here as b gets larger and larger and larger. So what we have is b going to infinity, and we have to be careful here. If we have b to the negative k plus 1, or b to any power at all, in fact, if the exponent is positive, and the exponent here is negative k plus 1, if it's positive, then we have positive numbers to positive powers. They'll get larger and larger and larger. b to the negative k plus 1 is going to shoot off towards infinity. However, if that exponent is negative, and sometimes it helps to write this out as an example on the side, if we had b to the negative 2, well, that would be a larger and larger number to a negative power. That's actually 1 over a large number, and that's going to head towards 0. b to the negative k plus 1 is going to head towards 0. This is the case we want because we were asked to find the values for which this converges or approaches a finite number, and that'll be the scenario we get with this. So we'll put that in here, 1 over negative k plus 1. This expression is going to approach 0. We'll add the conditions on that in a second, times minus 1. And that's true if we have negative k plus 1 being negative, or negative k plus 1 is less than 0, or if we swing things around, k is larger than 1. And that's in fact exactly what we were supposed to end up with. If we have integrals of t to high powers in the denominator, then this integral will converge. If we have t to low powers, powers less than 1 in the denominator, then this integral will diverge.